Okay, a few things up here to begin with. By the way, welcome to week number 9, I think it is. Homework 6 was going to be due tonight, but I actually extended it until Sunday, give you some extra time to work on it. We've talked about some of the problems, but not all of them. Maybe only about half of them, actually. So today we'll work on a lot of those Homework 6 questions. The first thing we'll do today, actually. And then you'll have the weekend to take a look at it. Homework 7 was going to be due a week from today, and it's mostly over chapter 6. So it says up here, homework 7 due after the exam. But ... The ... means there's going to be some that I want you to do before the test. And I'll let you know which ones those are based on how much we get done today. So although homework 7 is not due till after the second test, there's going to be a few of them that I think you should work on, before the test. Okay? And then Thursday lab is also going to be an online lab, so I'll send you an announcement tomorrow about that. So last Wednesday's class I didn't actually put up until just a little while ago. I left my video camera in Fort Wayne, unfortunately, and I finally got it back. So if you're looking for that video of last Wednesday's class, it wasn't there until today, but it's in the videos module now. Okay, I guess the big thing up here is exam 2 is actually next Wednesday, so you have a whole week until that. It's essentially over the last half of chapter 5, and then chapters 9 and 10, and maybe a little bit of 6, depending on how much we get finished today. Okay? That'll be about the 2/3 mark of the semester after next week. So by the weekend, hopefully I'll have a practice test up, and you'll have it for the weekend. We're not going to actually meet on Monday. I'll make a review video, give you lots of different hints and things like that over the weekend. So make sure you take a look at this video at least up by Monday. Try to work out the practice test on your own, see what questions come up, and then send me any emails that you have over the weekend and on Monday. And if you want to meet before the test personally, just send me an email. We can meet across the hall in 220, before class or whatever. I'm here pretty much all day on Wednesday, so if you want any one-on-one time, just let me know. Office hours. Okay? Or we could do a Zoom meeting, whatever you want. Okay, and then the second exam is on Wednesday. Same kind of thing, make your own formula sheet, both sides, put whatever you want on there. It'll be multiple choice, but you'll have to show your work, just like the first test. Okay, and then also next week, it's an in-person lab. So next week, Group A will be doing a lab called Human Arm Model, and we'll be modeling the bicep muscle. So Group B does not meet a week from Thursday. This is all next week stuff. And then the next week it'll be Group B, and Group A will have the week off. Okay? Any questions about any of the stuff I've already said? All right, very good. I feel like we're in pretty good shape with this test coming up. So I wanted to start off with some homework questions. And in doing so, we'll be able to review this stuff. So the first one is the 6th one on the homework. And it says the world's fastest human can reach a speed of 11 meters per second. In order to increase his gravitational potential energy by an amount equal to his kinetic energy at full speed, how high would a sprinter need to climb? So essentially we're taking the amount of kinetic energy that this sprinter has, go at 11 meters per second, and seeing how high the sprinter could actually climb if we were to take all that energy and turn it into gravitational potential energy. Okay? So it's an energy transformation problem. You might be worried that it doesn't give you the mass. But remember, if anything's ever going to cancel out, it's the mass. Okay? So it's not a mistake that they didn't give it to us. If you feel more comfortable, you could just pick a number and do it that way, but let's just see how this works out. So if I forget to hit the screen, yell. I'm not sure where Rick is at right now. Okay, good. So we're taking kinetic energy, Ke, and turning it into gravitational potential energy. Okay, so remember kinetic energy is 1/2 mv squared, and then gravitational potential energy is mgy. And there's where the m's actually cancel out, right? There's an m in kinetic energy, there's an m in gravitational potential energy. So the m's cancel out, and then we can solve for y. That's really what they're asking. It says on the homework h, but it means the same thing as y. So v squared over 2g turns out to be equal to y. Okay, and then we can put the numbers in. 11 meters per second, don't forget to square it, and then divided by 2 times 9.8. And if you notice, the units turn out to just be meters at the end. It's a good little check here. So 121 divided by 20, approximately, so you get an idea what it is. Let's get an exact number. Whoops. So 11 squared divided by 2 times 9.8, about 6.2 or so meters. So that's pretty good meter-wise, right? That's like 20, or that's about 20 feet in the air, a couple of stories. Okay. All right, good. So energy transformation, kinetic energy becoming gravitational potential energy. Any questions on that one? Okay. Let's go on to another one. And this is the 7th one on the homework. The elastic energy stored in your tendons can contribute up to 35% of your energy needs when you're running. So you can think of your tendons as kind of being like springs that stretch, so we're storing some energy there. Sports scientists have studied the change in length of the knee extensor tendon in sprinters and non-athletes, and they find on average sprinters' tendons stretch 43 millimeters, whereas non-athletes only stretch 33 millimeters. And I think you might have different numbers for this one. Okay, the spring constant for the tension and is the same for both groups, so 32 newtons per millimeter. That's what the spring constant is. What is the difference in maximum stored energy between sprinters and non-sprinters? Okay, so this tendon stretches. In doing so, we store some spring potential energy. They give you the spring constant. We want to see how much energy is stored for the athlete versus the non-athlete. And then the answer is the difference between those. Okay, good. Flip this around this way. Easier for me to write this way, hope you don't mind. So spring potential energy is 1/2 kx squared. Okay, so they actually give you the K. Just be careful of the units. 32 newtons per millimeter. And for the non-athlete, I'll just put the stretch for the non-athlete. This is 33 millimeters. And then for the athlete, that's what the little A means for the athlete, this is 43 millimeters. So maybe without going into a super amount of detail, I just want to show you how to set this up. So we can find the amount of spring potential energy for the non-athlete. This would be 1/2 kx for the non-athlete squared. Just be careful of the units. This is newtons per millimeter, this is millimeter. So right away I would change this into newtons per meter. I would change these numbers into meters. Do the same thing for the athlete. And then what they're actually asking is the difference. So take the spring potential energy of the athlete, that's what this is, spring potential energy, minus the spring potential energy of the non-athlete. So this is what they want. This is athlete, use the athlete numbers. This is non-athlete, use the non-athlete number. And again, I would turn this into meters. So, divide that by 1,000. Same thing here with the spring constant. Change this into meters. Remember, it's 1,000 millimeters per meter. Okay? So put those together, subtract it, and that's how much energy is, the difference in energy stored. All right, feel like you have a good idea about that one? All right, excellent, good. Okay, so when you skid to a stop on your bike, which you can't see, okay, so you skid to a stop on your bike. It's supposed to be nice out tomorrow, so maybe tomorrow will be the last chance, right? 74 degrees or something. That's what I'll be doing. You can significantly heat the small patch of tire that rubs against the road surface. Suppose a person skids to a stop by hitting the brakes on the back tire, which supports half of the 40 kilogram combined mass of the bike and the rider, leaving a skid mark that's 38 centimeters long. Assume a coefficient of kinetic friction of 0.8. Okay, so that goes back to chapter 5, this idea of coefficient of kinetic friction. As far as exam 2 goes, that's the kind of thing that might be in exam 2, this coefficient of kinetic friction. So we can start thinking about it already. How much thermal energy is deposited in the tire and the road surface? Okay, so the first problem we did today was kinetic energy, gravitational potential energy. The next one was spring potential energy. This one's thermal energy, and if you remember what we're doing now, thermal energy comes from the magnitude of the work done by friction. So that's what we'll have to figure out. How much work does friction do in this problem? Okay? So let's take a look at it. Okay, let's write down what we know here. So the back tire supports half of the 80 kilograms. So really the mass that we're worried about here is 40 kilograms. Coefficient of kinetic friction is 0.8. And this thing slides a distance of 38 centimeters. So be careful, you've got to put that into meters. Divide it by 100. And really how much thermal energy, or in other words, what is the magnitude of the work by friction? So the formula in the book looks like this. And then this is the magnitude of the work by friction. So this is perfectly good. We'll just have to actually write down what the magnitude of the work by friction is. It's the frictional force, and then times the distance that the frictional force acts over. And we just want the magnitude of this. Okay, so really this is what we're trying to figure out. Okay, so remember what kinetic friction is. It's the normal force times mu sub k. And in this example, the normal force is equal to the weight. So we've got mg times mu sub k. The reason being the normal force, again, is equal to the weight. Okay, so I can put all this stuff together then. Here's the frictional force, the kinetic frictional force. Multiply it by the distance. That'll give us the magnitude of the work done by friction. Right, the bike had some kinetic energy to begin with because it was moving. It stopped. What happened to it? Well, it became thermal energy. Okay, so we've got mg mu sub k times x. So 40 kilograms, 9.8 meters per second squared. Mu sub k is 0.8, and then x here is 0.38 meters. Okay, so kilogram meter per second squared, that is a Newton. I'm multiplying it by a meter. A Newton meter is a joule, so the units are good too. So 40 times 9.8 times 0.8 times 0.38. So about 119 or so joules. Technically, the work done by friction is negative, but we're just looking at the magnitude of that. That's why it's positive. All right, good. Yeah, whenever you're riding your bike, you always try to not to stop, right? Because you're turning your kinetic energy into thermal energy. Every time you have to hit your brakes, you are converting kinetic energy into heat that you can't utilize. So you always try to not stop if you can. Pull up to a stop sign and hopefully the people wave you through, right? So you don't have to stop. All right, good. Questions on this one? All right. So anyone planning on to go to medical school might see something like this. This is an MCAT problem. So remember, if you go to Mastering Physics, mostly you have the book there and the homework is there, but there's also something called the study area. So if you do hit the study area, you can check it out. They've got free MCAT quizzes that you can take for the physics part of it anyway. Okay, so that's there. You've already paid for it, so if you are planning on taking it, sometime you can take a look at the quizzes. So this is what it might look like anyway, and you don't get to use a calculator for that. When a flea, mass of 450 micrograms, is jumping, it extends its legs 0.5 millimeters and reaches a speed of 1 meter per second in that time. And how far can the flea jump, ignore air drag? So really this problem is saying the flea is taking kinetic energy and turning it into gravitational potential energy, just like the first problem we did today. So kinetic energy is becoming gravitational potential energy, and how high can the flea go? Okay, they do give you the mass here. It's not really a nice convenient number, 450 micrograms. So 450 times 10 to the minus 6th. But it turns out we don't actually need the mass to do this problem. All right, let's look at it. Good. I'll just try scooting it this time. Okay, so we're taking kinetic energy, turning it into gravitational potential energy. So 1/2 mv squared turns into mgy, and we're trying to figure out the y part of it. So the m actually cancels out. They give it to you, but you don't actually need it. Okay, so v squared over 2g is y. So how do you do this without a calculator? Well, luckily they gave you the speed as 1 meter per second. That's even easy to square, right? 1 times 1. So divided by 2, and then divided by 10. So a half divided by, so this would be a half divided by 10. And then we want the answer in millimeters. So 0.5 over 10 turns out to be 0.05. So that's how you could actually do it without a calculator. I just wanted to throw one of these MCAT ones in here for you, in case you're going to be taking it. Anybody taking it? Anytime? Okay. Maybe you will, maybe you won't in the future. A friend of mine, actually she was a student, now she's a friend of ours. She's just turned 30, having a baby. That doesn't really pertain to the story so much, but we just saw her for that reason at a baby shower. She became a doctor. She's a neurologist now. She went to Johns Hopkins and stuff like that. So you can go to P&W and become a doctor if you want to, right? Okay. On to the next one. In this one, what minimum speed does a 180 gram puck need to make it to the top of a frictionless ramp that's 4.9 meters long and inclined at 26 degrees? Okay, so another way of thinking about this is how much kinetic energy does the puck need at the bottom to be able to make it all the way up to the top. Because really that's what's going on here, right? We're taking kinetic energy and turning it into gravitational potential energy. It's just maybe a little bit trickier because they don't give you the height, they give you the angle and how far along the track is, but really we know that it matters with the height. So let's do a picture of this one and see what we can come up with. Okay, so what minimum speed, in other words, what is V, that 180 gram, so 0.18 kilograms, right, divide it by 1,000, make it to the top of a frictionless ramp. So if they say no friction, that means you don't have to worry about the work done by friction. It's a purely conservative type problem. You're turning one kind of energy into another kind. Okay, so the ramp is 4.9 meters long. We don't know what the height is, but we can figure that out. And the angle here is 26 degrees. Okay, so kinetic energy becoming gravitational potential energy, 1/2 mv squared equal to mgy. They give you the mass, but again, you don't need the mass, it cancels out. So kind of similar, we're trying to figure out what this speed is at the bottom. So turning kinetic energy in here into gravitational potential energy there. So v squared is 2gy, so then v is the square root of 2gy. So I'll leave it to you to get the y part, right? You know this, and you know the angle, so you can come up with y. A little bit of trig there. And you know, which one do you use? Sine, cosine, tangent? Well, I usually start with the sine. Sine of theta is y over the hypotenuse. So the sine of theta is actually the one to go with. And then you can solve for y there. Any questions on this one? So the online lab last week was this skate park one. Do you have any questions on that lab? I've just thought about it now with this picture. It's kind of a fun one where you can move things around on a computer screen, right? It's build your own tracks and that sort of thing. I think most people already submitted the lab, so it must have been okay, I thought. Okay. All right, well, if you do come up with any questions, just let me know. The computer's thinking. So this one, I don't want to actually do, but just say a couple words about it. The famous cliff divers of Acapulco leap from a perch 35 meters above the ocean. How fast are they moving when they reach the surface of the water? So this one is going in reverse, kind of. You've got gravitational potential energy at the top, and that's turning into kinetic energy right before the diver hits the surface. So just kind of do this one in reverse. Gravitational potential energy, mgy, turns into kinetic energy, and you can figure out how fast you're going at the bottom. Okay. And then the second part here, what happens to the kinetic energy as they slow and stop in the water? So I don't want to give that part away, but think about it. You had kinetic energy, what happened to it? Okay. Kind of like the bike tire. That'll be my hint. Okay. Okay, here's another one. A hockey puck is given an initial speed of 5.1. If the coefficient of kinetic friction between the puck and the ice is 0.05, how far does the puck slide before coming to rest? Solve this problem using conservation of energy. So we'll do it that way. Just remember on the test you could use whatever method you want to solve it. except for Googling. You can't Google it, right? Okay. So this puck has an initial speed of 5.1. You might have different numbers, so be careful. The coefficient of friction between the puck and the ice. Okay, so this is ice. It's a lot less than rubber on pavement that we saw earlier. This is 0.05. And then how far does it slide before coming to rest? Okay, good. Again, we don't have the mass, but let's just keep going and see if the mass cancels out. Chances are, again, if anything's going to, it's going to be the mass. So conservation of energy means we're turning kinetic energy in to thermal energy. So the book calls thermal energy delta E thermal. And this is the magnitude of the work done by friction, which is the force of friction times the distance that we're going through. Okay? So if you want, the picture looks something like this. Normal force, mg, here's friction back this direction. And the puck is moving that way. Okay, so it's this frictional force that slows the puck down. So the puck is sliding along. Somebody had to do something to get it to move at 5.1 to begin with. Maybe the hockey player hit the puck with a stick. It's going at 5.1, sliding across the rink. But there is friction, and it's going to stop. So again, we're turning kinetic energy into thermal energy, which is the work done by friction. So looking at this part and this part, we've got 1/2 mv squared. That's kinetic energy. Now the frictional force is the normal force times mu sub k. That's just the definition of kinetic friction. And then don't forget times x. And then from the picture, right now you're still thinking, oh man, I still don't know what m is. One more step will do it though. 1/2 mv squared, normal force equal to mg. Okay, there's where the m's going to cancel out. And then mu sub k times x. Okay, m's cancel out. And then the only thing that you don't know is x. So you have to do a little bit of algebra. We got a v squared over here. There's a 2 in the denominator. So I'll divide both sides by g times mu sub k. And there's the x. Okay, very good. Excellent. So in this one, you could have maybe figured out what the frictional force actually was. Try to figure out the acceleration somehow, and then from that, use kinematics. This is a lot quicker, though. Okay. Any questions on this one? A little tricky. All right, very good. All right, very good. Here's some fun stuff coming up. So ball 1 with mass 130 grams is traveling at 12 meters per second, collides head-on with ball 2, which has a mass of 330 grams, but it's initially at rest. So be careful. The mass is in grams. We'll just see how that goes. I guess to me, whenever I see grams or millimeters or centimeters, it's like a warning sign, right? Like, oh, okay, not SI units. Let's proceed with caution. What is the final velocity of 1 if the collision is perfectly elastic? So perfectly elastic means that the initial kinetic energy is equal to the final kinetic energy. In the collision lab, that was the case where they interacted via magnets, right? It was a nice gentle collision. So that means the initial kinetic energy is equal to the final kinetic energy. Sort of the opposite of that collision is the one where they stick together. So we don't have the stick together one yet. This is just a nice, perfectly elastic collision. And then let's see what part B actually is here. What is the final velocity of 2 if it's perfectly elastic? And then what's the final velocity if it's perfectly inelastic? What happens if they stick together? Okay, so this is really from chapter 9, this problem. All right, so let's write some of these things down. Okay, so mass 1, I'm going to put it in the kilograms. It was 130 grams, so that's 0.13 kilograms. Mass 2, oh, and this one was initially traveling at 12 meters per second. So mass 1, velocity 1 initial, before the collision, that means 12. Mass 2, 330 grams or 0.33 kilograms. Initially has a speed of, oh, it's at rest. Okay, good. So from the notes that I put up on Monday, I came up with an equation that will predict velocity 1 final and velocity 2 final if this one's at rest, just based on the initial velocity of the first one and the two masses. You do that by looking at conservation of kinetic energy and conservation of, for this special case, and conservation of momentum. So from the video you saw this. Whoops. Okay. Mass 1 minus mass 2 times V1 initial over M1 plus M2. And for the other one, this was 2M1. Yep. Mass 1 plus mass 2 divided by times V1 initial. So this is just a special case. These equations are not in general true. This is only for a collision between two masses that's perfectly elastic and the second one is not moving to begin with. This is what we did in the lab, remember? We had a stationary mass, and then we sent the other mass at it. They collided via magnets, and we could predict what their final speeds would be. So let's see if this actually makes any sense. Now, do you remember the one, mass 1 would come in if they had roughly the same mass? So mass 1, mass 2. Mass 2 stationary, mass 1 came in. They have the same mass. That's the one where this one would stop and this one would keep going. Do you remember that one? So if they have the same mass 1 and mass 2 are equal to each other, V1 final should be 0. And in the lab it actually was, right? V1 came in, that one just went away. So this one stopped, so that makes sense. If you also remember, if this one came in with a certain speed and it stopped, this one would leave with approximately the same speed. And that makes sense too, because 2m1 divided by really 2m1 means V2 final should be equal to V1 initial. So that worked out as well. We also did the case where mass 2 was bigger than mass 1. So if that's true, if mass 2 is bigger than mass 1, V1 final turns out to be negative. So M2 bigger than M1, V1 final is negative, it turns around and heads back the other way. So this one's bigger than this one, comes in, bounces back. That's the one that we did in the lab too. Okay, so what you saw in the lab is represented in these equations here. So what you can do then, we won't put the numbers in, but here's how you solve for V1 final. You have everything here. Right, here's the masses, here's V1 initial. Just take this and put it in here. Take this stuff and put it in here. Okay? And that will give you the final speeds of each of them. I included this problem because it really is just what we did in the lab. Now the other collision we did in the lab, right, so this is part A, I think, and that's part B. The other collision we did was the stick-together collision. So part C really, part C and part D are the same answer, right, because it's stuck together. They want the final speed of 1 if they're stuck together. Oh, sorry. Part C and D, there, finally. Part C and D will be the same answer because it's asking what's the speed of 1 if they're stuck together, what's the speed of 2 if they are stuck together. Well, they're stuck together, so they have the same speed. Back to the document cam. So for part C and D, it's going to be the same answer. And basically the initial momentum is equal to the final momentum. They're stuck together, there's no conservation of kinetic energy, anything like that. No matter what kind of collision though, remember the initial momentum is equal to the final momentum. So this would be mass 1, velocity 1 initial. Now the author of the book would write mass 2, velocity 2 initial, but velocity 2 initial is 0, so that's going to be 0, so I don't write it down. And then when they're stuck together, they have a common mass. Remember, we did that in chapter 9. And then you can solve for this common speed. So the big V there means the common speed. So divided by mass 1 plus mass 2. Okay, and you can put those numbers in as well. Okay, excellent. Any questions on C or D? Great. And then the last thing on the notes was this idea of power. So power is how fast you could do work or how fast you consume energy. So in this one, 1,100 kilogram sports car accelerates from 0 to 31 meters per second in only 11 seconds. What's the power, the average power of the engine? So power is joules per second, and a joule per second is a watt. So on my bicycle, I can, if I'm going down a hill, I can get up to 31 meters per second. It's going to take me a lot longer than 11 seconds though. So let's pick a different number, 0 to 20. I can do that on my bicycle if it's flat. It's going to take me a lot longer to go from 0 to 20 than a sports car can, because a sports car can provide that energy a lot faster than I can. Okay? I should have said 0 to 10 if it's meters per second. I can't go 0 to 20 meters per second on my bicycle. Okay. So let's take a look at this one. Just be careful, the answer is in kilowatts, by the way. So power would be the amount of the change in energy, however we want to write it, divided by the amount of time. So the change in energy here is just really a change in kinetic energy divided by the time. So this would be the final kinetic energy minus the initial kinetic energy divided by time. So 1/2 mv final squared minus 1/2 mv initial squared, and then divided by the time. And I think we're starting from rest actually, yeah, so this term is 0. Okay, so put the numbers in. You're going to have a different mass and speed probably, but this many joules divided by this much time, a watt is a joule per second. The only thing to be careful is they want the answer in kilowatts. So you'll have to divide your answer by 1,000 to put it into kilowatts, right? 1,000 watts per 1 kilowatt. Maybe a better way of thinking about this is if you go to the tech building, you run up the steps, you gain a certain amount of gravitational potential energy. Or you could take the long windy path to the front door. You get the same amount of energy at the end, it just took you longer, so it's less power. Depends on how you feel that day, right? If you're feeling full of energy, run up the steps. If not, just go around the other way. You don't use energy as fast. Same amount of energy, but just that time factor comes into play when you're talking about power. Okay, good. So that's the last one really from homework 6. Any questions on homework 6? So you have until Sunday, send me an email if you run into any problems. We can work it out over the weekend. Okay, if not, then we'll move on to the next chapter. Actually, kind of going backwards. We're going back to chapter 6. So circular motion. When we do talk about chapter 6, we'll have to talk just a little bit about chapter 3. So chapter 3 was two-dimensional motion. And really, going in a circle is two-dimensional motion. You're not just going in a straight line this way or that way. You're going that way and this way at the same time. So it's two-dimensional motion. So whenever you go in a circle, there has to be a force towards the center. If there's not, then you can't go in a circle. So the moon goes around the Earth. There's a force on the moon from the Earth, the force of gravity. That's what keeps the moon going in a circle. If that gravity just disappeared, the moon would just continue on the way that it was going. If you're spinning a kid in a circle, actually there's a picture of this coming up. Okay, so yeah, here's a good picture. What happens if the guy lets go of the kid? It becomes projectile motion, probably, right? The kid would just go off in the direction that the kid was already going. It's the force on the kid from the guy here that keeps the kid actually going in a circle. The kid, from the kid's perspective, it feels like the kid's being thrown away from the circle. That's because the kid would normally be going that way anyway. There has to be a force on the kid towards the center to actually allow the kid to go in a circle. If you have a ball on the end of a string and you're going around your head like this horizontal circle, if you cut the string, the ball is just going to go the way it was going to go anyway. It's the tension in the string that allows the ball to go in a circle in the first place. So there always has to be a force towards the center. Okay, so really this chapter could be called The Search for the Force Towards the Center. So here's a fun ride. The riders feel pushed out. This isn't a real force, it just feels like it. Really there has to be a force towards the center. Here it's the normal force on the back of the riders towards the center that keeps them actually going in a circle. There's a fun ride at the Porter County Fair. I'm sure it's at other fairs too. You go in a horizontal circle with your back against the wall, basically. So this is a circle, you're part of the circle. I think they maybe make you take your shoes off. I don't know for sure. It gets going really fast and the bottom falls away. And you don't fall to the ground. You keep going in a circle because of the frictional force on your back. And the force towards the center is the normal force on the wall. So the faster you go, the bigger the normal force is. The bigger the normal force, the bigger the frictional force is, and you can stay stationary that way. Anybody ever do that ride before? Okay, yeah, a few people. I keep saying I'm going to do it, but I never have, so maybe I'll put it on my bucket list. It's kind of a low threshold, I guess, but got to start somewhere. When it's a satellite going around the Earth, it's the force of gravity that's towards the center. So we'll get a more detailed look at the force of gravity. For us, we've been calling it mg. It's actually more complicated than that. Weight being equal to mg works really well at the surface of the Earth, but if you start to go away from the surface, it's not as accurate. So we've been kind of using an approximation of Newton's law of gravity, one of the 4 fundamental force laws. Okay, so circular motion, and then the last part of the chapter is a little bit with gravity and orbits. Okay. So before that, we've got to go back to chapter 3 a little bit. So you can go in a circle at a constant speed, and there's still an acceleration. So be careful, that's a common misconception. Well, if the speed's constant, the acceleration is 0. But if you're going in a circle, the direction keeps changing. That's why there is an acceleration. So whenever you go in a circle, you have an acceleration, so then you have to have a net force. Okay, so let's take a look at some vectors here. There's one up here, one down to the left. Let me actually highlight these. So So you got the velocity here, a velocity here, velocity here. So the speed is constant because the magnitude of this is not changing, but the direction keeps changing. So there has to be an acceleration towards the center whenever this happens. It's called centripetal acceleration, as you can see here. Sometimes it's called radial acceleration, along the radius towards the center. Okay, so that just means towards the center. In this class, we'll just do constant speed going in a circle. It doesn't have to be like that. You could have situations where you have something actually speeding up. So for the time being anyway, constant speed. But there is a change in velocity because the direction's changing. So say you're going from point 1 to point 2. This is the displacement here. For angle theta, that's the radius, that's the radius. So here's V1 and here's V2. We're going through this so I can show you what the magnitude of the acceleration is going to be. We could look at these similar triangles. Before we do that, let's just do it like this. So here's V1, V2, here's delta V, the change in velocity. So if you did V2 minus V1, you draw the resultant from the head of V1 to the tail, to the head of, from the tail goes here on V1, the head goes up here to the head of this one. Okay, so we'll compare this one to this one. So we know delta V over V, so this is to this. Same magnitudes, we're just looking at the magnitudes. So it's V1 and V2, they're just calling it V down here. It's the same thing. So delta V, this side is to this side as, so equals, in other words, as the displacement is to R. So this is what you saw in the previous slide. This is just a little derivation going on. This is perfectly good. You could also write d, this distance, as v times delta t. Remember, v is equal to d over delta t. And you can take this and plug it in here for d. And that's what's being done in this step. So we still have delta v over v, d over r, but now d is v times delta t, and still divided by r. Do a little bit of algebra. Move the delta t over to the left-hand side, move the v over to the right-hand side, and you get delta v over t. That's really what the acceleration is, right? Change in velocity divided by the time is v squared over r. Good, so this is the centripetal acceleration, the magnitude of it. V squared over r. So we'll use that a lot. And it's directed towards the center of the circle. So again, centripetal acceleration, sometimes called radial acceleration, it just means towards the center. So it's always going to be towards the center, and that's the magnitude of it. Okay, good. That's really the part of chapter 3 that we didn't do at the time. I wanted to save it until we did chapter 6, though. Good, so that's something you can put in your physics tool belt now. Okay, let's see what we can do with this. A toy car moves around a circular track at a constant speed. If suddenly it suddenly doubles its speed and changed by a factor of 2, what happens to the centripetal acceleration? Okay, so let's think about this. So this, excuse my writing here, radial acceleration, I'm calling it, centripetal acceleration, whatever you want to, v squared over r. So they're saying, what happens if you make v twice as big? The lights just change? Oh. Okay, there we go. So if you make v twice as big, what happens to the acceleration? So think about it, and then we can then vote on it. Okay, good. So this would be like A, B, C, D, and E. And if you don't have your card with you, you could use like, 1 for A, 2 for B. Okay, so suddenly you make V twice as big, leaving R the same. What happens to the acceleration? Okay, good. Excellent. Yeah, a little bit tricky, but it's actually 4 times as big, right? If you make the velocity twice as big, it's squared in the formula, right? So V is squared. If you suddenly make V twice as big, you'd have 2V. You got to square it, so then you have 4 times what it would normally be. Okay, good. So it's the acceleration is proportional to V squared. All right, good. Here's an example we can take a look at. World-class female short track speed skaters can cover 500 meters in 45 seconds. The most challenging elements of the race are the turns, which are very tight with a radius of 11 meters. Estimate the magnitude of the skater's centripetal acceleration in each turn. So you go through 500 meters in 45 seconds. You go through a radius which is really small, 11 meters, a really tight turn. Estimate the magnitude of the skater's centripetal acceleration in each turn. And if you ever watch this, they actually go down like that, right? Okay. If you're on your bicycle going through a turn and it's a tight turn, you really got to kind of try not to do too tight of a turn. You might fall over, right? The reason is you've got to have a really big force towards the center because you have a big acceleration if the radius is small. So we can estimate the speed that we have. So, and that's what this symbol means, approximate. Take the total distance divided by the total time, 11 meters per second. Okay, it says here the speed varies during the race, but you can make a good estimate of the speed by using, just take the total distance divided by the total time. If it was literally your job to do this, you'd probably figure out a different way, but this is an approximate way of doing it. Okay, so we can figure out the acceleration in the curve then. The formula is V squared divided by R. We'll use 11 for V divided by the radius, which is also 11. Okay, the math is nice on that. Turns out to be 11 meters per second squared. That's the acceleration in the curves then. It's quite large, more than G, but you can see from the picture the skaters are leaning, because it's a big amount there. If you go too fast, you won't be able to make that turn, right? So you got to negotiate the curve at a rate that's not too great, or you won't be able to make the turn. Okay, any questions on that one? Okay, here's another one. Turning a corner on a typical large intersection in a city means driving your car through a circular arc with a radius of 25 meters. So you make a turn, and we're estimating that if that were part of a circle, the radius would be 25 meters. If the maximum advisable acceleration of your vehicle through a turn on wet pavement is 4 times 9.8, so, 0.4 times 9.8, what's the maximum speed you should drive through this turn? Okay, so pretend you're doing this too. You're going through a turn, and maybe it's just been raining. You can't go as fast, right, or you'll slide out. You have to be able to have enough force towards the center to be able to actually go through that turn. Okay, so let's work this one out. Okay, so the radius of the turn here, they're telling us is 25 meters, and they're telling us the radial acceleration. So centripetal, radial, same thing. I always call it radial because it reminds me that it's along the radius towards the center. So this is 0.4 times 9.8. So with this in mind and this in mind, how fast could you actually go? That's what they're asking us. Okay. So here's all we have for this radial acceleration right now. V squared over r. Okay, and they're asking for v, but they're giving us this and this. So radial acceleration times r is v squared, and then take the square root of both sides to get v. Okay, so 0.4 times 9.8, and then times 25. So you can see the units are going to come out to be, it's meters squared over seconds squared. Take the square root of that, gives us back to meters. Okay, good. Let's see what we get. 0.4 times 9.8 times 25. Then I gotta take the square root of that. So on my calculator, I just raise it to the half power. Same thing. So about 9.9. So around 20 miles per hour. Okay. Go too fast, you're not going to be able to make the turn. Now that's especially true in the winter, right? When it's icy and snowy out, you really have to go slow around turns. Hopefully we won't actually experience that for a while. Unless you like snow, then I hope it snows for you. Okay. Any questions on that one? So I have a note here to do 3.38. So that's from homework 7. Okay. So to withstand g-forces up to 10 g's caused by sudden pulling out of a deep dive, fighter pilots train on a humid centrifuge. So 10 g's is 98 meters per second squared. So imagine that you're a fighter pilot, you're going through like a big dive like this, you're going through a dive like that, so there's got to be a force towards the center because the dive is part of a circle. To do that, you have got something like 98 G's, which, 10 G's, which is 98 meters per second squared. To simulate this, we've got a centrifuge. So maybe from biology or chemistry, you've used a centrifuge. Anybody done that yet? Okay, good. So it's something that goes in a circle really quick to separate things out by mass usually. So in this humid centrifuge, that's what this is, the length of the arm is 12 meters. Okay, so there's an arm that extends from that wall to me. I'm sitting in a centrifuge, and it's going to go around in a circle really fast till I get up to 10 G's. And what's the speed? What speed am I moving at 10 G's? So the question is, why are they doing this to the fighter pilots? Well, different things happen at different G's. Over a certain limit, the blood is not in your head anymore, and there's different symptoms that occur. First, you just start seeing things in black and white. So you're going through a dive, and you lose the blood from your brain going through a dive. So it's pulling in your legs, basically. You start to see things in black and white, and eventually you could black out, and that's not good when you're flying an airplane. So different things. People wear compression suits on their legs to keep their blood from pooling in their legs, different things like that. So this is a test to see what's going to happen to this fighter pilot to avoid those scenarios I just talked about. Okay, so how fast do we have to go if we want to simulate 10 G's? So in this one, they're telling us this acceleration is 98 meters per second squared. That's 10 G's. The arm here is 12 meters. And how fast do we have to go? So really, it's the same question as we had before. The previous one was, here's the acceleration, here's the radius, how fast. So we ended up with this formula. I really want to know how fast this is, so let's use that formula and see what the speed actually